Let's build a machine learning model to predict the possibility of heart disease. Today, we're building a supervised machine learning classifier that learns from past patient records to predict whether heart disease is present or not present in a new patient. The data we're using today is a UCI heart disease dataset where each row represents one patient and each column is a measured feature like their age, cholesterol, resting blood pressure, chest pain type, and so on and so forth. And there is one final column called num that is not a feature but the diagnosis for the patient. Its outcome is coded as an integer where 0 means heart disease is not present and 1 through 4 mean heart disease is present at increasing levels of severity. Today we're using a winner-takes-all method, which is a simple model selection strategy where you train more than one candidate model on the same dataset, evaluate each candidate on the same evaluation data, and choose exactly one winner to keep and toss the rest. Now let's actually get coding. As always, we start by importing all of our dependencies, and today we have NumPy for math, Pandas for data, and a bunch of tools from scikit-learn to make our machine learning model work. Next, we're loading in the data by reading the CSV file into a data frame so that the model can access it. Then we create a target variable y from the original num column. Because our goal is to predict presence versus non-presence, the code converts num into a binary label. It sets y to 0 whenever num itself is at 0, but sets y to 1 whenever num is greater than 0, so that the model's job becomes a clean yes or no classification problem. And then we create the feature matrix X using the data frame but dropping the target column y so that the model doesn't accidentally learn from the answer sheet. Now we're ready to split our code into training and testing data using a stratified split. A stratified split means the code tries to keep the same proportion of positive and negative cases similar in both sets. And this matters because heart disease datasets are often somewhat imbalanced. And if the split accidentally makes one side have far more positive cases than the other, then your evaluation will become misleading. We're designating 80% of the dataset for the training data, which the model can learn from and find patterns in, and leaving the other percent for the testing data, which we will use to evaluate the model's performance on unseen data. Next, we move on to preprocessing, and this block exists because most datasets have missing values and mixed data types when most machine learning models expect clean numeric inputs. This code separates all the columns into numerical columns and categorical columns based on their data type, and then defines two small pipelines. The numeric column fills in all the missing values with the median of the column and then scales all the numbers so that they have a comparable magnitude. The categorical pipeline fills in the missing values using the most common category or the mode, and one-hot encodes the category. One-hot encoding takes a categorical column like chest pain type and turns it into a multitude of zeros and ones so that the model can refer to it mathematically. The column transformer here is the piece that applies the numeric transformation to the numeric columns and the categorical transformation to the categorical columns. And the result is a single transformed feature matrix that is ready for a classifier. Wrapping the preprocessing and the classifier into one pipeline is important because it ensures that the same transformations learned from the training data are applied to the validation data. It prevents data leakage that could come from accidentally scaling using information from the testing set. Here's where we're actually defining our two candidate classification models. Logistic regression is a linear classifier that learns a weighted sum of features and passes them through a sigmoid curve to output a probability between 0 and 1. And this makes it very easy to see how the risk of heart disease goes up as the level of a certain feature increases or decreases. Then we have a random forest, which is a tree-based model that builds many decision trees on randomized samples of the training data. In our case, we're building 600 of them. And this model can capture nonlinear relationships and feature interactions that a linear model can miss. Here we have an evaluation function, which trains the models on the training data and computes the predictions on the inputs of the testing data. It first reports the accuracy, which is the number of correct yes or no predictions at a certain threshold, which is usually 0.5. It also reports ROC-AUC, which summarizes the ranking quality across all of the thresholds and prints a confusion matrix and classification report so you can see how many false positives and false negatives there were. Here are the evaluation metrics for the logistic regression model, and these are the evaluation metrics for the random forest model. Their performances are obviously extremely similar, but the random forest does have a higher ROC-AUC, so the model selects it as the winning model. And this is the model we'll use going forward to have the best possible performance. Finally, the cross-validation block takes that winning model and evaluates it on multiple training and validation folds across the full dataset. This step is checking how reliable our winning model is and how much its performance varies depending on which examples tend to fall into the validation set. Now we can actually apply this in a real-life scenario. In this block of code, we're just selecting a random row from the dataset and using our model. This random row here describes a 60-year-old male from Cleveland with all of these features. And the probability of heart disease here is over 98%, so the model predicts that heart disease is present. Just for fun, here's a correlation heat map of all our features and the disease, and here are the top 15 most important features according to the Random Forest. And that is a fully functional, simple model selection machine learning method to predict heart disease. So if you learned something from this video, don't forget to save it for later and follow for more.